students, we have completed our chapters 2 in the last lecture. It was approximate methods of analysis, and this time we are going to start new chapter, that is modeling of distribution system components. In this particular chapter we will see the modeling of various components in the distribution system, starting from distribution feeders, then transformers, regulators, capacitor banks and loads, and distributed generator also. So in today's lecture, that is lecture number 10, we will start with series impedance of distribution lines and feeders. So how to calculate series impedance, that particular thing we will see in this particular lecture. Before going to this lecture, just revise what we have seen in chapter 2. As I told you, chapter 2 is basically on approximate methods of analysis of distribution system. In that chapter particularly we have seen two factors, those are K drop factor and K rise factor, and we have seen that K drop factor is nothing but percent voltage drop per kVA per kilometer, and it is basically used to find out limit of loading of your distribution system, or to find out voltage drops in the distribution system, or you can say if you want to find out the conductor size, the K drop factor will be useful. Similarly, we have seen that the K rise factor. K rise factor is basically percent voltage rise per kVAR per kilometer. So this is basically useful for placement of capacitor, that is nothing but finding the location of the capacitor or size of the capacitor in distribution system. Then we have seen uniformly distributed load and their modeling, means if there is uniformly distributed load, how we can find the lumped model of them to find out the voltage drop and power loss. These are the approximate values of voltage drops and power loss. Then we have seen exact lumped model of uniformly distributed loads. After that we have seen lumped model for various geometrical configurations, particularly rectangular configuration and triangular configurations. Now let us start with this new chapter, which is basically calculation of series impedance of your overhead conductors or feeders. So we know that different types of materials are used for conductor. Those are basically copper and aluminum, and nowadays since aluminum is cheaper and lighter, it is widely used. However, aluminum, as shown it here, aluminum is less conductive and it is having less tensile strength. Means long conductor will be requiring a higher tensile strength because we are hanging them between the tower. To increase the tensile strength, we use ACSR conductor. Those are nothing but aluminum conductor with steel reinforcement, which I have written there. Then there is AAC conductor, which is all aluminum conductors. Then triple AC conductor, those are all aluminum alloy conductors. And then there are aluminum conductor with alloy reinforcement. So these are alloy reinforcement is basically to increase the tensile strength of the material. Out of these there are other types also, but out of these all types ACSR are widely used. So structure of ACSR conductor is like there are aluminum strands and steel strand. So steel strand will be at the middle, which are basically give to increase the tensile strength, and the aluminum conductor which are at the outer part, they are basically to carry the load current. Okay, so as we know, resistance is calculated by using this formula, where this rho T is actually resistivity of the conductor material, this is length of the conductor and area of the cross section of the conductor. And as we know that resistivity of the material is temperature dependent, so resistance will also change whenever temperature is changing. So if you want to calculate resistance at different temperatures, you can use this formula. So if you know the resistance at one temperature, resistance at another temperature can be calculated using this formula, where this alpha 0 is known as temperature coefficient of resistance. If that is known, resistance can be calculated at any temperature. However, we have seen that our actual conductor is not a single conductor. Earlier formula was applicable for only the single conductor. However, if there are many strands in the conductor, like I shown it here, we can calculate the resistance like this. I shown it here. So, resistance is given by again rho L by a same formula, resistivity, length of the conductor, cross sectional area. Now, since there are many strands of aluminum, let us say there are ns number of strands and each strand has cross sectional area of As. So, overall cross section area of aluminum will be given by ns multiplied by As. Now, this cross sectional area of one strand will be given by this formula, where ds is diameter of one strand. So, this is nothing but overall cross sectional area of one strand of aluminum conductor, and this is nothing but I am taking for length of the conductor. So, I am considering 1 kilometer length. So, actually I have to take 1000 meters because this formula is valid for 1000. So, length is 1000 meters. Instead of 1000 meter, I have just taken 1050 meters, because we have seen that in case of stranded conductor we twist it, or in case of ACSR conductor there is twisting of conductor, and because of that twisting length of the conductor will increase. So, approximately to accommodate that increased length, we have taken this 50 meter extra for considering the twisting. So, if you can take all these constants together, I will get 1337 here, and these are the remaining variables which will give me resistance of ACSR or stranded conductor for different strands. However, generally data of all these types of conductor, that is ACSR or AAC or AAA, data sheets will be available, and data sheets will be giving you lot of data. So, one of the data sheets I have shown it here, where this first column shows the code word for the conductor, and these code words are generally given the names of birds or animals. So, these are the code words of your conductor, and then required data of each conductor is given here. So, you can see that this gives size in AWG or kilo circular meals, and then there are actually aluminum strands. These are the number of strands and diameter of each strand. Then steel, there is only one strand, and this is diameter of steel strand. Then total cross sectional area of the conductor out of this aluminum area. Then this gives me resistance values of this conductor at different temperatures for 1000 feet. So, we can easily calculate for 1 kilometer at various temperatures of the conductor. Then this gives amplicity of the conductor, and this gives you geometric mean radius of that particular conductor. And we know that geometric mean radius of the conductor will be required for while calculating the inductance of the conductor. So, resistance will be available from data sheets. Let us see how we can calculate inductance of the line, and we have already seen the inductance formula for transposed line. So, we know that this is your formula, which is 2 into 10 raised to minus 7 natural log of GMD by GMR, or we say instead of GMD sometimes they say D equivalent, and this GMD or D equivalent is given by cube root of DAB plus DAB multiplied by DBC multiplied by DCA, and these are nothing but the distance between the conductors. In that case, line impedance for 1 kilometer in ohms at 50 hertz can be calculated like this. So, it will be total impedance will be resistance plus j omega into inductance. Resistance we can get it from the data sheets, and inductance can be calculated from this part, or reactance can be calculated from this part. This is your omega, this is your inductance, and since I am considering per kilometer, I have to multiply it by 1000 because this formula is gives me inductance in Henry per meter. So, to convert into kilometer, you have to multiply it by 1000. Now, if we take this coefficient together, it comes out to be 0.0628 natural log of GMD by GMR. So, resistance we can get from data sheets, and we can get the reactance part using this equation. However, we have seen that our distribution lines are generally untransposed because they are short length line, and transposition only done if the length of the line is longer. So, in case of distribution feeders, they are generally untransposed. So, if there are untransposed feeders and if there are n conductors in the system, then there will be n by n matrix because there will be a self inductance, mutual inductances, we have to take them separately. If they are transposed, we mention it together. So, in case of untransposed line, we need to calculate self inductance and mutual inductance. Let us see how we can calculate self inductance of the conductor, and that self inductance we can calculate from the self linkages, self flux linkages. So, flux linkages lambda II are nothing but flux linkages of conductor I due to its own current I. So, due to current II, and this is given by 2 into 10 raised to minus 7 natural log of 1 divided by GMR of that particular conductor, which will be in Webers. And if you calculate inductance, which you know that flux linkages divided by current will give me inductance, and if you divide this formula by II current, you will get this equation, that is 2 into 10 raised to minus 7 natural log of 1 divided by GMRI, and this will give me self inductance of that conductor. And then you can easily calculate your self impedance of that conductor by again same formula here. So, here also we will get this same constant, that is 0.0628 natural log of 1 divided by GMRI. Okay, self impedance of the conductor will be given by this formula. Let us see how to calculate mutual inductance. So, for mutual inductance, I am considering here flux linkages due to current Ij. So, flux linkages of conductor I due to current in conductor J. So, any conductor J, the current is Ij here, and flux linkages of conductor I due to current J is given by this formula, which is 2 into 10 raised to minus 7 natural log of 1 divided by Dij. Dij is nothing but distance between conductor I and J. Then inductance, mutual inductance between these two conductors will be given by this flux linkages divided by your current. So, if you divide this equation by Ij, you will get 2 into 10 raised to minus 7 natural log of 1 divided by Dij, where distance Dij is distance between the two conductors. Then we can calculate the mutual impedance. In this case, resistance will not be there. So, it will be just j omega Lij. So, this is your omega, this is your Lij, which you are derived. In this case, okay, here also there is this is Dij into 1000 ohm per kilometer. So, finally, you will have this formula here, which will give me mutual impedance between the two conductors. So, in summary, we have seen that in case of transposed line, we have only one impedance value, which is given by this equation here, and in case of untransposed line, as I told you, we will be having n by n matrix if there are n number of conductors into the system, and these n entries of n by n matrix will be given by this formula, where this Zii will give you self impedances of those conductor, and Zij will give you mutual impedances between the conductors. Like one system which I have shown it here, where suppose there are 3 conductors, then there will be 3 by 3 matrix for for untransposed line, and entries of those 3 by 3 matrices will be given by this one. So, these ZAA, ZBB and ZCC will be calculated using this formula here, which is given ZII, and the remaining entries are calculated by using this formula Zij. Till now we have seen that we can calculate the impedance of distribution line if they are transposed or untransposed. In case transposed, we are getting one impedance only. In case of untransposed, we are getting matrix of n by n size if there are n number of conductors, and we also seen that how to calculate those entries. However, these formulas are applicable if there is no ground return current. Okay. Basically, if you see this particular figure here, generally what happens whenever there is unbalance into current, that unbalanced current will flow to the earth. So, if there is no neutral, there are 2-3 different conditions. So, in this condition we are considering 3-phase 3-wire system where there is no return path through the neutral wire. In that case, if the grounding system is here and then a substation grounding is here, in that case your unbalanced current or zero sequence current will actually flow to the earth path and it will come here. Now, when this current is flowing to the earth will act as a one conductor, and already there are these 3 conductors, and because of earth current there will be mutual impedances between this earth current and all these current. Now, problem here is that we do not know what is the resistivity of the earth, because it will not be uniform everywhere, and whenever current is flowing to the earth, the path of the current is also not definite. So, current will take any path which is available. Let us see what effect it happens. Before that, we will just see 2 different systems. Let us say this is another system. In this case, there is multi-grounded neutral. So, it is 3-phase 4-wire system. However, grounding is done at different places. So, this is your 3 phases and this is neutral conductor. So, unbalanced current will take path through your neutral wire, as well as some current will also flow to the ground, because this is having multi grounded neutral. So, the current which is zero sequence current will take path through both these conductors, that is neutral conductor as well as ground conductor. In another case, there is possibility that the grounding is not there, multiple grounding is not there, only single grounding is there. So, in that case, whole unbalanced current will actually flow only through neutral, because we are not grounding the system at this place. So, whole unbalanced current will actually flow through the system. So, in that case there will not be earth current, but earlier 2 cases there will be some earth current, and because earth will act as a conductor, it will be having mutual impedances with all phase conductors, and considering those mutual impedances or calculating those mutual impedances will be very difficult task. So, we will see how we can consider the effect of current which is flowing to the ground. Let us say you are having these 2 conductors. This is one conductor I, another conductor is say J. ZII is self impedance of conductor I, ZZ is self impedance of conductor J, and ZIJ is mutual impedance between them. Now, I am considering the ground also has one conductor, because it is carrying your unbalanced neutral current. In that case, earth will act as another conductor. So, there will be 3 conductors, and ZDD will be your self impedance of earth, ZD will be mutual impedance between conductor J and earth, and ZID will be mutual impedance between conductor I and earth. So, all the mutual impedances and self impedances are shown there. Let us say this conductor I is carrying current II and conductor J is carrying current IJ, and then the II plus your IJ current will be flowing through this. It will get added at this point, and then II plus Ij current will be flowing to the ground. And I am considering this ID current which is flowing through ground, means I can say your ID current will be equal to minus II minus Ij. Let us say I want to calculate voltage Vig, that is nothing but voltage of this terminal with respect to ground terminal at this place. So, I am interested in calculating this voltage drop here, which is Vig. So, this voltage drop will consist voltage drop across this, then voltage drop across this branch, and if you see this voltage drop across this branch will be due to all the three currents. So, it will be Zii into Ii, which is a self drop, then drop in Zij, which is due to current Ij. So, it will be Zij into Ij plus drop due to current Id, which is Zid into Id. So, this is nothing but drop which is happening into this due to all the three currents. Then there will be drop which is happening in this branch due to all the three currents. So, it will be minus, because this drop we are taking in this direction and Id current is flowing in opposite direction, there will be minus sign here. So, it will be Zdd into Id, which is due to self current and self impedance, Zid into Ii due to current Ij, Zjd into Ij due to current Ij. So, total drop across these 2 points will be given by this equation. Now, as I told you, your Id current will be just Ii current minus Ii current minus your Ij current. So, it will be minus Ii minus Ij. So, instead of Id I can put minus Ii minus Ij. Here also there is Id, instead of that I can put minus Ii minus Ij here, and then I have taken all the terms which are related to Ii and Ij together. So, the terms which are related to Ii, there are 4 terms which are related to Ii, I have taken it together. So, this I will get this term, and if I take current terms to related to Ij together, I will get this term, and this term I am calling Zii cap. So, this total term of 4 impedance adding I am calling Zii cap, and here I am calling Zij cap, which is addition of all these 4 impedances. Now, let us see what is meaning of all these 4 impedances which you are adding. So, let us take only this term which is Zii cap. So, if I take this term here, Zii cap, which will be consisting of 4 impedances which are shown in that figure. Now, Zii will be consisting of resistance of the conductor plus reactance of the conductor. Zdd will be nothing but resistance of the earth and reactance of the earth. Zdi will not be having resistive part, so it will be having only reactance, and Zid also will be having, since it is mutual, it will be having only reactance Z. So, this J will not be there. So, Xid plus J Xdi. In this case also there will not be J. Similarly, another term Zij will be having these 4 terms which I explained in last slide. In this case also this Zij will be having only reactance term. Zdd will be having resistance of the earth plus reactance of the earth, and this is nothing but your mutual impedances, that is why only reactance terms are there. Now, let us expand this first term Zii. As I explained you are having, this is your Zii 2 terms, this is your 2 terms related to Zdd, this is term related to Zdi, and this is related to Zig, this J will not be there. So, I have just taken resistance term together, that is Ri and Rd, and then reactances term together, which are basically this one. And in this case xii, we already seen that we can get the inductance of the conductors using the GMR information of the conductor, and you can get the reactance of the earth by using the GMR information of the earth, and then this is nothing but distance between earth conductor to the conductor I. This is nothing but again distance between the earth conductor to conductor I. And just in this case this term will be easily available because GMR of the conductor will be available. However, if you see these three terms, GMR of earth, it is very difficult to get GMR of the earth. We will see that why it is, because as I told you, when the current is flowing through the earth, it is taking many different paths and this earth is not uniform. So, whenever we are considering earth as a conductor which is having very enormous dimensions, and because of that GMR of earth is very difficult to get. So, we don't know this quantity. Similarly, since we do not know the conductor as a earth as a conductor where it is lying inside the earth, we do not know what is distance between earth conductor to the conductor I. So, this term is also not known, this term is also not known. Okay. So, what I did here, I have taken the terms which are unknown together and the term which is known here. So, basically this term is unknown here. Similarly, we do not know this term. Similarly, resistance of the earth is also difficult to get exact value. So, this is difficult. Okay. So, other things we can calculate. So, however, these two terms it is difficult to get if there is earth return current. Also, now consider another term which is Zij, which we have written. There are again 4 terms we listed down in the last slide. In this case also Zij will be having only reactance, Zdd will be having resistance of the earth as well as reactance of the earth, and these two terms will be again, since they are mutual, they will be having reactances only. Then again we can take the resistance out of this, and then this is real part and then this is your imaginary part, and this represent your Xij, which you can, as I told you, which is nothing but mutual impedance between the lines, which you have seen that we can get it from the distance between the two conductors, that is 1 upon Dij into 2 into 10 raised to minus 7, which gives me reactance or you can say self impedance of the conductor. This is nothing but again your GMR of ground. This is nothing but distance between ground to conductor J, and this is again distance between conductor I to ground conductor. As I told you, since the earth is having enormous dimensions, getting these GMR of earth or distance between earth conductor to the conductor I, conductor J will be difficult. So, again these 3 terms will be unknown to us. So, in this case also these known terms I have taken together. So, this is your known term. However, this unknown term, by integrating these logarithms together, this is your unknown term, and in this case also this Rd, which is unknown. One more thing you can observe, that Zij is nothing but mutual impedance between the conductor, while we are considering earth return also taken into account. In that case, you can see that in mutual impedance term also getting small resistive term here. Okay. And as I told you, it is very difficult to get these unknown quantities which I explained in this slide directly, and which is very kind of tedious task, because earth will be having, we can say, layers of the conductors. So, there will be lots of conductors in the below the earth surface, which can be modeled conductors like this, which will be in infinite in numbers. So, that is why getting GMR of the conductor or getting the distance between earth conductor to the phase conductors will be a difficult task. So, in summary, we have started the chapter number 3, which is modeling of distribution system components, and we have started with first component, that is distribution feeders and distribution lines, and we have started with calculation of impedance of these distribution lines or feeders. And then we have seen different types of conductors. We have seen how to get the resistance of the conductor, how to calculate it, and then we have also seen that how we can get this resistance value from the data sheets. Then we have seen the inductance of transpose distribution line, impedance also we have seen, and then inductance and impedance of untransposed line, which will be having, if there are n number of conductor, it will be having n by n matrix. However, in case of transposed line, there will be only one entry or only one number. Then we have seen impedance of distribution line with earth return. So, we have seen that in case of earth return, some current flows through the ground, and because of that ground current, the earth will be acting as one of the conductor, and there will be mutual coupling between the phase conductors to this earth conductor, and it will make calculation of your impedance a little bit tedious. So, in next class we will see that how we can take this earth return into account. Thank you.